Okay, got that going. So, reminder of the two biggest things that we talked about last time. First off, the Church-Turing thesis, which essentially says we now have a definition of algorithm. Our definition of algorithm is whatever a Turing machine can do. That's what we mean from algorithm from here on out. And from here on out, all we basically really care about are algorithms. We only use Turing machines as a means for talking about algorithms, but it's algorithms that we're essentially interested in. And then the other crucial point that came up in Turing's paper was his implementation of a universal Turing machine. So we didn't go over it explicitly, but he does in his paper, he goes over how you can build what's called a universal Turing machine. He lays out all the states, the diagrams, the transitions, everything, to build this machine U. And what is his universal Turing machine able to do? What it's able to do is take as an input some other Turing machine M and some input string W, and it's able to simulate W on M. So this is basically theoretically proving that you can have software run on hardware. You can simulate some program with some input on some other Turing machine. So that's what his universal Turing machine would do. It would run some input on the machine where it would just accept if M accepted, and it would reject if M rejected. Now, you kind of missed a bunch of our hierarchy of languages. So we start out by talking about the simplest languages you can talk about, which are regular languages. These are languages that can be recognized by regular expressions. Then we went to context-free grammars. You ever do a compilers course? So compilers, grammars, are in this class right here, context-free grammars. If you remember coming up with your rules for plugging in, if you see this, plug it in with this string, that's exactly what a grammar is. And then decidable languages. These are the languages that Turing machines can decide. What that means is it's possible for me to write an algorithm such that given some set, to everything in the set, my algorithm can say, yes, it belongs in the set, and to everything in the set, my algorithm can say, no, it doesn't belong in the set. The example we used last time was solutions to Diophantine equations. So we talked about how if I gave you a Diophantine equation, it's possible for you to write an algorithm that finds solutions, but if I gave you a Diophantine equation that had no solutions, there's no way that you could write an algorithm that concluded, yeah, it doesn't have any solutions. Not a general algorithm. So Diophantine equations are an example of something that's not decidable here. But we could recognize solutions, that's recognizable. So recognizable, to give you intuition, is it's possible to create an algorithm that can check if an answer is correct. Decidable is you can write an algorithm that can check if an answer is correct and also check if it's incorrect. And so that's our hierarchy of languages. Every regular language is a context-free language, is a decidable language, is a recognizable language. So that's a recap from last time. And so now the next section, we're jumping into decidable languages. Languages that are decidable. And we're going to go over a bunch of examples showing how we're going to prove that a language is decidable, proving that a Turing machine can recognize a language. So start with the acceptance problems for DFAs. In your compilers class, you might have had to write some of these, some state machines like this. So simple state machine here, this is an example of a DFA. So here's its start state, here's its accept state. You start out here. If you read a 0, you move to this state. If you read another 0, you move to this state. Read a 0, move to this state, etc. And so it will accept if we read an odd number of zeros. It will reject if we read a non-odd number of zeros, or in this case, an even number of zeros. So here's an example of a simple DFA. Here's an example of a string that it would accept. If I got rid of one of those zeros, it would not accept that string. Ah, he's here.
Sorry for that. I was driving home from the ER, so.
Oh, geez.
Yeah. The text message will look confusing because normally what you do is you say, hey, is anyone coming? And then you say, okay, we're doing it, or we're not. And I didn't get that message.
I thought I only said it if we're not doing it. But I could be more perfect. Sorry about that.
No, it's fine. It's just that. So I wasn't sure. I should have reached out and double checked. But okay.
Yeah, I could be more careful. Okay. Well, you basically just missed the recap from last time.
Oh, great.
Just starting new stuff. So we're going to start with what's called the acceptance problems for DFA. And the question we're trying to answer is, can we determine if a given DFA, we'll call it D, will accept a particular string, call it W? So here's an example of an easy DFA, one that just recognizes an odd number of zeros. Here's an example of an input string that would happen to accept. So what we're looking at the set A sub DFA. This is a set, remember when we put those brackets there, then it's an encoding of the object. It's converting the object to string. So D is a DFA, W some string, do some encoding, so that the whole thing's a string now, because languages are always strings. So it's a set of all encodings of some DFA and some string W, where D is a DFA that accepts input W. So an example of something in here would be the encoding of this DFA together with this string. If I got rid of the 0, then the encoding of this DFA and this string would not be in there. So this is a set of all possible DFAs that accept, it's all combinations of DFAs and W's where that DFA accepts that W. So this is an absurdly massive set. And the question is, can we create a Turing machine that recognizes a set? Can we create a Turing machine where no matter if you give it an encoding of a DFA and some input string W, the Turing machine can say, yes, this DFA will accept this string, or no, this DFA will not accept this string. Can we create a Turing machine that does that? That's essentially what we're asking here. That's equivalent to asking, is the acceptance problem for DFAs decidable? Called the acceptance problem because we're determining, does that DFA accept that string W? So, the answer is yes, and we're going to prove it. So theorem 4.1, we're going to prove that the acceptance problems for DFAs is decidable. This set here is a decidable set. We can create a Turing machine that says yes when it's in there and no when it's not there. And it's pretty straightforward. So we let M1, this is going to be a Turing machine, let M1 equal, and now we're just going to give our high-level description of what we do. On input DW, so D's are DFA, W's are input string, we simulate W on D. Now we know from last time that it's possible to build a universal Turing machine which is capable of simulating an input on a Turing machine. A DFA is just a really, really dumbed down version of a Turing machine. So if it's possible for me to simulate a string on a Turing machine, it's definitely possible for me to simulate a string on just a DFA. There's like a Turing machine that's just being real stupid with its memory. So we know that this is definitely possible. The way that we're able to justify that statement is because Alan Turing told us how to create this universal Turing machine. That's how we justify it. All right, so we simulate W on D. Now, we're guaranteed that when we run an input string on a DFA, it eventually terminates. There's no such thing as a DFA running forever. If I run this string on this DFA, it transitions through the states however many times. Once it's done reading the input, our DFA is done running. It's not like a Turing machine where it can keep accessing its memory over and over again and there's no way of knowing when it will stop. So we're guaranteed that if you run some input on a DFA, it eventually stops. And when it stops, it will either be in an accept state or it won't. We're guaranteed that. So we just simulate W on D. If D ends in accept state, we accept. Otherwise, we reject. Since M1 decides that language, a DFA, then a DFA, the acceptance clause for DFA is a decidable language. And the only real gotcha there that you have to think about is how this statement is justified, which came from that.
So the input string is always eventually finite, supposedly.
Yes, every input string will always be finite. Okay, so good with that. Next one. Alright, so next now we're going to look at the acceptance problems for NFAs, non-deterministic finite automata. So the acceptance problems for NFAs, this set is going to be the set of all encodings of an NFA and a string W, where N is an NFA, accepting the string W. We're going to prove that's decidable. How do we do that? First off, let M2 equal, on input, we give it the encoding of an NFA and some string W. We know, we've proven earlier, that every NFA has an equivalent DFA. And there's a procedure for converting an NFA to a DFA, and we went through that process. So we know that there is already a procedure out there for converting an NFA to a DFA. And since a procedure is an algorithm, we know there's some algorithm to do it, therefore we know our Turing machine can do it. So we know our Turing machine can convert some NFA to an equivalent DFA, call it D. Now that we have a DFA instead of an NFA, we can just run on M1, the machine we described up here, we can take that basically as a subroutine and plug it in down here. So now on the machine we described up there, I can now give it the new DFA that I just converted N to, and the same input string that I was given here. And now if this D accepts that W, then this N would have accepted that W, if and only if. So we run with that DFA and that input string on M1, and we accept if M1 accepts, otherwise we reject. And then, since M2 decides that language, then that's a decidable language. Next theorem. We won't bother proving this one because it's the same exact type of thinking. But let A be the set. It's the acceptance problem for regular expressions. So let this be the set of all encodings of R and W, where R is a regular expression that generates the string W. R is a regular expression, and it's able to generate W. We'll prove that's decidable. How would we prove that? We've already shown earlier that every regular expression has a logically equivalent DFA. And we've already shown a procedure for converting regular expressions to DFAs. And so it's identical to this, we just replace all our N's with R's for the regular expression. We have our regular expression, we can convert our regular expression to the DFA, and then we can run the string on the DFA. That would only accept it if the regular expression could have generated it. So, same thinking there. So, there's a bunch of different acceptance problems. Now we're going to move on to what's called an emptiness problem. Oh, did you have a question? No. Okay. So, now we're going to do the emptiness problem for DFAs. What's the emptiness problem? The emptiness problem asks, if you give me a DFA, does this DFA accept no strings? Or in other words, its language is empty. So let me give you an example of a DFA that doesn't accept any strings. Here's one. It doesn't have an accept state. Or, I put some other state over here, Q2, that just goes to itself on 0. And that's the accept state. There's no way for me from the start state to get to the accept state. There's another one. So, is it possible that given some arbitrary DFA, we can come up with some procedure for determining whether or not it accepts nothing? Its language is empty. So that's what this is. That's what this says. So the emptiness problem for DFAs is a set of all encoding of DFAs such that D is the DFA whose language, remember L parentheses D, that's a shorthand for the language of D, is equal to the empty set. So let's prove that that's decidable. Where I used M2. I don't know if I reference this somewhere down the road. But I need to call it M3 because M2 was one here. So I have to pay attention if I use this down the road. Don't remember if I do. Anyways, so let the Turing machine M3 equal this description. What's it going to do? On input, some encoding of a DFA. What we're going to do is we're first going to mark the start state of the machine. So here's an example of one that we know accepts nothing. So first we mark the start state of the machine. Doesn't matter how we do that. Some symbol. Maybe the state again with an X through it. So first we mark the start state of the machine. Then we mark every state that has a transition from an already marked state. Let me make this one just a little bit more complex. Let's pretend that we had Q2 here, and that was connected. And then Q3 over here, disconnected. So we still know that this does not accept any strings, just using our intuition looking at it. So first step was to mark the start state. There we go, we marked the start state. Next, we mark every state that has a transition from an already marked state. So this has a transition from an already marked state, so we mark that. Step 3, repeat 2 until no new state is marked. So repeat 2, we mark that. Repeat 2, there's nothing else to mark. So that finishes 3. 4, except if no except state is marked, otherwise reject. The except state is not marked, so we say yes, this is an empty language.
So if it is marked in any way, then it's not.
If it was marked in any way, then there would have had to have been a transition to it that ultimately went back to the start state, which means that there would have been some path
that you could.
that led to it. So there would have been some string that it accepted.
So you're essentially just doing like a depth, well, I guess like a breadth first search to see if an accept state exists within the graph. If you think of the DFA as a graph, which you fairly easily can.
Kind of. It's not necessarily a breadth first search because we're not belling out whenever we come across an accept state. We could have done that. We're going through everything and then just checking in the end. So yeah, we're not caring about efficiency here. All we care about is proving, is it possible? But yeah, we could have done a breadth first search for an accept state and that would have been fine. Okay, oh, we were right here. Okay, that procedure makes sense?
Yeah, I guess so.
Cool. Alright, let's do the next one. The equality problem for DFAs. What's the equality problem for DFAs? So this set is a set of all encodings of pairs of DFAs such that the language of the first DFA is equal to the language of the second DFA. In other words, 2 DFAs that accept the exact same strings. Give a quick example of something like that. I can scribble it over here. So we could have had the DFA like this. Here's its start state. On 0 goes over here, except 0 goes back. Or we could have had the DFA that looked like this thing. And make this an accept state, make this an accept state. And we could have had 0 goes here, 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 0 goes here. So in some sense, these are the same DFAs, because they always accept the same strings. They both read input 0, now they're both in accept state. They read input 0, now they're both in a reject state. They both read 0, now they're in accept state, etc. So that's what we're talking about. Is it possible to build some algorithm that no matter what 2 DFAs you give it, it can always say, yes, they accept the exact same language, or no, they don't? And the answer is yes, we can, and we'll show how to do that. Okay, so this one, first thing we need to do is we're going to define this new language A, and for this we have to remember our closure properties for regular languages, which kind of sucks for you, because you didn't see that. But what we proved last time is that regular languages are closed under complement. So if I have a regular language and I take its complement, it's still a regular language. We proved that regular languages were closed under union. If I have 2 regular languages, I union them together, still a regular language. And we proved that regular languages are closed under under intersection. 2 regular languages intersecting, still regular language. So what do we have here? Remember, these are DFAs, so their languages are regular. Regular language, regular language, regular language, regular language. So I let A be this monstrosity. The first thing to notice is that A is a regular language, since it's just a complement, union, and intersection of regular languages. That's the first thing to know. And now let's make sense of what this is saying. What is A going to be equal to? It's going to be all the strings accepted by the first DFA and not the second one, or accepted by the second DFA and not the first one. It's also what we call the symmetric difference. Let's get a Venn diagram picture of this thing. If these are the strings accepted by D1, and these are the strings accepted by D2, then we're doing the language of D1 and not D2. So the language of D1 and not D2, that's all of this. Union together with the language that's not D1 and is D2. Not D1 and is D2, that's this. And you've also seen this as, sometimes it's written D1, a delta symbol D2, symmetric difference. Everything in this set that's not in this set, and everything in this set that's not in this set. Now notice, if D1 and D2 happen to be the exact same set, what does that look like? So if D1 and D2 are the exact same set, so here's D1 and D2, we do all the strings in D1 that aren't in D2, that's nothing, together with all the strings in D2 that aren't in D1, that's nothing. So their symmetric difference, if they're the exact same set, then their symmetric difference is the empty set. So D1, D2 equals the empty set. And this is just a fancy way of writing their symmetric difference. That's its definition.
Okay, so it's the outers of both D1 and D2 are you saying is the same?
So if D1 and D2 are the exact same set,
Yes.
their symmetric difference is the empty set. So we can reduce the question, because ultimately we want to know, are these the same language? And we need a way to check that. And so checking if these are the same language is the same thing as checking, is their symmetric difference the empty set?
Remind me what you mean by symmetric difference.
So the symmetric difference of two sets is everything in the first set that's not in the second set, together with everything in the second set that's not in the first set. So with the picture I have up here, the symmetric difference is these highlighted portions. Notice it doesn't include their overlap.
Right.
So if all they have is overlap, if the two sets are identical, then the symmetric difference includes nothing. It's empty.
Interesting.
So that's what this is. A, we set to be the symmetric difference between the two languages. If the languages are identical, A is going to be the empty set. So now we know that these two languages are equal if and only if A is the empty set. So now all we need to do is test to see if A is the empty set.
That's the part that I'm not connecting, is if the symmetric difference, or if they have a symmetric
Sorry,
difference.
I should probably be saying language of D1 and language of D2.
What I'm trying to understand is how does the fact that they are a symmetric difference make them the same, or the language equivalent, or whatever?
So I'm saying, you're going to write me a program. Here's what's going to happen in the program. I'm going to give you two sets, and I want you to tell me yes or no, these sets are the exact same thing.
Okay.
You only have three operations available to you. You can union the two sets together, you can intersect the two sets, or you can take the complement of the set. So if, when you perform this monstrosity of a calculation here, it comes out the empty set, then this set and this set were equal.
Just don't understand how it makes them equal, the fact that they have a symmetric difference.
If their symmetric difference is the empty set, then they're equal. Let's go over their symmetric.
Oh, so the opposite of that. Well, okay, so if they don't have any difference, then they're
If their difference is zero,
okay.
then they're the same.
I got
Yes.
I thought you were saying the other way around. That's why it's confusing.
Okay. No, you gotta say it until it clicks and then it feels obvious.
Yep.
Okay. So that's what this is basically saying. Take their difference. This is their difference. So A is their difference. If they're identical, A is the empty set, or zero in set, the zeros of sets. Okay. So we define A to be the difference of these two sets. And since A is a regular language, we know that there must exist some DFA that recognizes that language. That's the definition of a regular language. A language is regular if and only if it's possible to construct some DFA. What does it look like? Who knows? But a language is regular if and only if it's possible to construct some DFA that recognizes that language. So since A, by definition, is just a bunch of unions, intersections, and complements of what we know are regular languages, A has to be regular. Since A is regular, there must exist some DFA, D, such that the language of D is equal to A. With me? Okay. Now what do we do? Now we just use this machine we described right here. We let M, this is going to be M4 now. M4, sorry, screw my subscripts here, this one, and this is M3. So we're going to construct some new machine M4 now, and we're going to give it the input D1 and D2. So these are the two DFAs, and we're checking, do these accept the exact same strings? Step 1 is to construct D as defined up here, as described in 1. So I can take the symmetric difference of their languages, then create the DFA that recognizes that thing. So construct D, and then simulate D on M2. That should be M3. M3 being the machine we defined in the previous problem. What's M3? If you give it some DFA, it checks, is its language empty? That's what M3 does. So we already wrote some subroutine that checks to see if a DFA generates an empty language. So we take our DFA that we just constructed, and we run it on M3. If M3 accepts, then our language was empty. So we accept if M3 does, because D's language being empty is logically equivalent to those two being the same DFA. D's language, or A, being empty, is identical to D1 and D2 generating the same language. So big picture one more time, what do? We're given two DFAs. We look at the language, that's their symmetric difference. And we create the DFA, call it D, that recognizes that language. So the language of D is the symmetric difference of these two. We simulate D on this machine that we wrote before that checks to see if its language is empty. So we run D on M3. If M3 says D's empty, then that means the difference was empty. So if M3 accepts, then the difference was 0. So they're the same language.
Which is what you just barely explained.
Yes.
Oh, okay.
Just trying a bunch of ways until it syncs.
I got it, yeah. That makes
Okay,
sense.
perfect. So then M4 decides the equality problem for DFAs. There's our routine or our algorithm for doing it.
So using that logic, it's always basically finding the inverse of the accept states, basically. Where all the times where it would succeed, it is now all the places where it would fail is the symmetric difference. Is that kind of what you're doing?
No.
Okay.
What exactly is the set L of D1? Like, is that what Partly said? It's all the cases it would succeed.
L of D1, so if we were looking at this machine here, if this whole machine right here were D1, the language of D1 would be the string, oh, that one doesn't accept anything.
But it would be all the strings.
All the strings that make it end in an accept state. So if we went back to this super simple example that we had, where we have, here's our start state, here's our accept state. If you read a 0, go to the accept. If you read a 0 again, go back to start. This would accept the string just 0. If I just run 0 on this thing, we end the accept state. But it also accepts the string 0, 0, 0. First 0 takes us to here, second to there, third to there. So it accepts 0, 0, 0. So if we call this machine right here D1, then the language of D1 is equal to a set of all strings it would accept, which is 0, 0, 0, 0, dot, 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 goes on forever. There's an infinite number. So that's the language of the machine D1, similar for the language of the machine D2.
Now, so the symmetric difference would be basically all of the even numbers instead of all the odds.
Symmetric difference, you need to find two sets. So you can't take a symmetric difference with just one set. You're thinking of the complement. The complement of a set is everything not in it.
Remind me what complement means in this case.
So complement, that's what we use that symbol for.
Oh, the not, right.
The not. So maybe that's where you're getting confused with. So if we're just talking about if our alphabet's just zeros, then yes, the complement of this set would be all the even length strings.
So that would be almost outside your circles, is what you're referring to.
Well, it's just its own operation. It happens to be using the definition of a symmetric difference, but don't confuse the two.
Yeah. Well, so in the abstract concept of these circles, everything inside that circle is everything that it would accept. Everything outside that circle is what it would not accept, like even numbers.
Right, we're thinking about these as dots. So one of these dots right here represents the string 0. And another one of these dots represents the string 0, 0, 0.
Right. So all of those are all the odd numbers are in that circle. Now you have two different languages, possibly.
Yeah.
And they're saying in some cases they're identical. Their inputs are identical. In some cases they're not. And they either have to all be equal, or the circles have to like literally be perfectly where everything that would come out this way would come out the same way for one machine as it would the other. It makes them what's the?
So if we think about this as all the odd length strings, so this has 0, 3, 5, etc. And we think about this as all the strings whose zeros are a multiple of 3.
Yes.
So then 3 zeros is right here. 6 zeros is over here. And then 1 0, 3 zeros, and 5 zeros is over here.
Yeah, perfect.
So the symmetric difference would just be all the odd multiples of 3. So 3, not 6. 9, not 12. 15, not 18. That's what would end up in here in that case.
Oh, okay, so that's where I also got confused. I was thinking the symmetric difference was the circles outside of the intersection. But now I can see, when you say symmetric difference, you're referring to...
Oh, sorry. You're right.
Oh.
Yeah. What you just said is correct. The symmetric difference, I said that backwards. Symmetric difference is everything not in there.
Oh, so symmetric is difference
So
is everything that's not intersecting.
Right.
Oh.
It's everything but the intersection. And so when they completely intersect, when there's only an intersection, then the difference is 0. Or the empty set.
Yep.
Okay. So we take two languages, look at their symmetric difference. If it comes out the empty set, they're the same language. So we take our two languages, we take our two machines, we look at their languages, we take their symmetric difference. This is just saying, hey, the symmetric difference is still a regular language. That's all we were justifying there. So we take the language of these two machines, look at their symmetric difference, which is still a regular language, and run it through M3 to see if it's empty. If the symmetric difference came out empty, they're the same.
It's so funny because I literally came up with the exact same problem just today, having to completely rebuild a file, but I wanted the exact same output, but it's done differently. And it's kind of exactly, and what I did is I ended up building a test that just ran both of them, and then checked to make sure that the outputs were exactly the same. Kind of similar concept.
Yeah. Okay, so hit click there. Think we got it? Cool. Okay, so now upgrading from talking about DFAs to talking about context-free grammars. Remind ourselves again of what these grammars are, and we also, I don't know if we say anything about Chomsky normal form here, but we eventually need to mention it. So remind ourselves of a grammar. I can have something like S goes to 0, A, 1, and I can have something like A goes to 0, 0, or A goes to the empty string. So we start with S, and we're looking at the strings that can be generated by S. Sorry, I meant to do this. S or A. So S can go back to itself, doing a 0, 1, or it can go straight to A. So I might do S replaces itself with 0, S1. Now I still need to replace my S with something. This time I'll just replace it with an A. So now we got 0, A1. Now I have a choice. Do I replace my A with 0, 0 or the empty string? I'll choose the empty string. So 0, 1 is one possible string that we could have generated with this grammar.
Yeah, that's true.
Okay. So context-free grammars, we're looking at things like that. Our first problem is going to be the acceptance problem for context-free grammars. So what is this set going to be? It's going to be the set of all the encodings of a grammar and a string where that grammar can generate that string. So one example would be the encoding of this grammar with the string 0, 1. Since with this grammar, it's possible to generate the string 0, 1. Okay. So A is the set of all those. We're going to show that it's decidable. Oh, we do talk about Chomsky normal form here. So let's remind ourselves about Chomsky normal form. We get a grammar in Chomsky normal form where all our rules are of the form a variable goes to two variables, we'll do A, B, or a variable goes to a terminal. So that's Chomsky normal form.
Was it that only some of these can turn to be converted into
Every
Chomsky?
context-free grammar can be converted into Chomsky normal form version of it.
Oh.
So we could take this grammar and we can convert it into a Chomsky normal form. It just gets pretty big and hairy pretty quick.
I see.
Maybe we should have A can also go to AA, or A can go to just 0. Just like we can generate an infinite number of strings with this.
If I understand correctly, one of them you can't have, that would not be Chomsky normal form in that case, but
This is Chomsky normal form.
it is.
We have a variable goes to either two variables, or a variable goes to just a terminal.
I thought that it was only one variable to one terminal.
One variable to one terminal.
Oh.
Oh, you might be right in the sense that we might actually need a C here, and then C goes to 0. You're right.
I vaguely remember something like that.
But then that's not 2. Jeez. How can I do this off the top of my head? Oh well, we'll do CC. Okay, Chomsky normal form. And let's know something nice about Chomsky normal form. Let's go through generating a string here, and we'll set it up as like a parse tree. So we always start with just a symbol S. We can have symbol S, and it goes and it replaces itself with AB. I can have this A replaces itself with AA, and this B, let's pretend that this also had a, I don't know, AA. I can't make this work nicely. Maybe rather than generate an example, just explain it. So we start with our start variable, and our start variable in Chomsky normal form always has one of two options. It can either generate two variables, so I can either take my one variable and replace it with two variables, or I could take my variable and replace it with just a terminal symbol. So in this case, I take my start variable, replace it with two other variables, pretend those are variables. And then I can have those two variables each replace themselves with two variables, which are all variables. And then I can finally go through and replace them all with terminals, which would just be giving each one child. And then we would have our terminals. And so your parse trees are always going to look like this. It's either going to be splitting off 2, 2, 2 underneath, as you're replacing a variable with more variables, until you're finally ready to replace it all with your terminal symbols.
Oh yeah, that's all coming back to me now.
Yeah, I really want to come up with one example here that just works nicely. S goes to AB. We'll say A goes to CC. We'll say B goes to CC.
Isn't there also the empty string ability? That would be
Or
something.
AA. Things like these can also cycle back to themselves to make sure we can get infinite strings. And then we'll say C goes to 0. Okay, this is a really ugly way of saying it's going to be all the strings that have 2 zeros. So 2 or 4 or 6 or 8 zeros. So we start out with S here. S. We can replace S with A and B. We can take the A and we can replace that with the CC. We can take the B and replace that with the CC. And then finally, our C's we can go and replace with zeros. So when you replace with variables, you're always doubling. and then until you finally get to terminals, and you're replacing with 1. What this guarantees us, and the important thing about Chomsky normal form, is if I ultimately generate a string of length 4, my parse tree, the number of steps that it took me to generate that string, could have at most had 3 steps in it.
How do you find that out again?
Since it's doubling every time, then it's basically the log base 2 of the number.
Oh yeah, okay.
Not sure I said that right. Let me just think for a second. So we could start with this, have that go like that. We could have that go like that, like that. So for a string of 8, then it should be log base 2 of 8 plus 1, is what it is. Okay, so that's what we need to remind ourselves of. 2n minus 1. We're overthinking with that. I can explain this without looking at that picture, just with understanding the rules of Chomsky normal form. Okay, so let's go back to this now. So the acceptance problem for context-free grammars, it's a set of all grammars in strings W where G can ultimately generate that string W through some substitution, some sort of generation process. And we're going to show it's decidable. So we're creating a new machine now, M5, not M4. M5, what's it going to do? It's going to get some grammar G and some input string W. First thing we're going to do is convert G to Chomsky normal form. Now, when the grammar is in Chomsky normal form, and I'm creating one of these generation strings, so forget the parse tree, but just actually look at what the string looks like. So we start out with S, which just has one symbol in it. Now, the only thing I can do is replace S with AB. So after one step, my string grew by size 1. So S went to AB. Now in my next step, I can either replace A with 2 variables or B with 2 variables. But the point is, whichever one of those I do, let's say in this case I choose to replace B with, I don't know, BB. So now it's A, B, B. Every step we do, our string's just going to grow by length 1. So for the next one, maybe I replace that B with a CC, or we replace the middle B with a CC, so we'll say A, C, C, B. And we'll keep going, dot, 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 until we start replacing this thing with zeros. And let's say before we replace it with zeros, obviously we're just going to have a bunch of C's, C, 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 5, 6, 7, 8. And now it would take me 8 steps to slowly replace all those C's with zeros. Replace that with a 0, then that, then that, then that, then that. So, in general, what's important to notice? If we have an input string W, and it has length n, not input string, but the string we're checking to see if we can generate, like the string 8 zeros in this case. So if our string were 8 zeros, we look at the length of that string, which is just 8. All we have to do is list out all the possible combinations of the thing that happen in 16 minus 1 steps or 15 steps. There's going to be 7 steps in growing S to C, 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 because every time you replace a variable, you just add on 1 variable. So in getting S to 8 C's is going to take 7 steps. Because every time we replace a variable, we just add 1 variable. So 7 steps to get the length of my variables, and then 8 steps after that to switch all those to zeros. So n minus 1 steps to create all the variables for your string, and then n steps to switch out all those variables with their terminals.
2n minus 1 or just n minus 1?
N plus n minus 1. Which is 2n minus 1. So notice, replacing S with 8 C's here would take us 7 steps. And in that special case would have been 8. It took us 8 minus 1, 7 steps. And then replacing all these C's with zeros would take us 8 steps, or n steps. So n minus 1 to get all the variables, and then n again to replace our variables with terminals. And that's where we get the 2n minus 1. So if it is possible for some Chomsky normal form grammar to generate the string 0, 0, 0, 0, 3, 4, 5, 6, 7, 8. If it's possible for this grammar to generate this string, all I have to do is check all the possible ways that grammar could grow for 15 steps. Now that might turn into some massive number, but we don't care about efficiency, we just care about possibility. It's possible to do that. You can build some algorithm that just churns away every possible combination. So, since there's only a finite number of combinations that we have to check, we check those finite number of combinations. Or in other words, what do? We generate all the strings that our grammar generates, that our grammar G generates in 2n minus 1 steps, or at least one step in case it's the empty string. But typically you don't really need to think about that. And then if it generated the string W, if W is listed somewhere, we accept, otherwise we reject. So we got our grammar. We generate all the possible strings that we can do in 2n minus 1 or less steps. Look at all those strings. If any of them were the string W, then it's possible for that grammar to generate that string W. If none of them were that string W, then that grammar can't generate that string W. Because if it could, it would have done it in 2n minus 1 steps.
Nice.
That's the way it works.
That's useful to just know that it's got to end.
Yeah, it's got to end. You know you're guaranteed to reach an end in this many steps, so only try for this many steps. If you didn't get it, it's not possible.
That's cool. It's really cool.
Okay, so that was the acceptance problem for context-free grammars. Now let's look at the emptiness problem for context-free grammars. Can we determine if a grammar is empty? Now let's make up some grammar here. We've got one written right here. Let's make one that we know is empty as well. We'll say S goes to AB. We'll say A just goes to AA. We'll say B goes to BB. And we'll say C goes to 0 or 1. So since it's impossible to get from our start symbol, we're assuming that our language is a string that's binary strings, zeros and ones. Those are strings we're talking about. So since it's impossible to get from our start symbol to zeros and ones, then we know that the language of this grammar is going to be empty. However, if I replace that C with a A here, well, first let's do the C, then we'll replace it with an A, see why we still have a problem, and then we'll fix it and make so that we don't have a problem anymore. So first off, obviously we can see that this grammar, starting from here, I can't generate any strings of zeros and ones. Because I can only replace AS with A's and B's, and A's and B's with A's and B's. And C is the only thing that can give me zeros or ones. Okay, so let's walk through the process here, and then we'll come back to a concrete example. So let the emptiness problem for context-free grammars be the set of all grammars such that the language of that grammar is the empty set. It doesn't generate any strings. We're going to prove that this is a decidable language. We're going to create our Turing machine M. What's it going to do? On input of some encoding of a grammar G. First thing it's going to do is it's going to look at that grammar, and it's going to mark all the terminal symbols. So it's going to come through and mark the terminal symbols. In our case, we're assuming strings of zeros and ones. It's going to mark 0, and it's going to mark 1. Mark all the terminal symbols. Then for every rule of the form A goes to whatever, mark A if all the whatevers are all marked. So since everything C can go to here is marked, we're now going to mark C. Make sense so far?
Yes.
Okay. Now we repeat step 2 until no new symbols are marked. So now I come back and I mark every symbol if it's a terminal or if everything to its right has been marked. We're done. Didn't change anything. Okay, so repeat 2 until nothing new is marked. Nothing new is marked. Now we accept if the start symbol is not marked. Our start symbol is not marked, therefore we accept. This generates an empty language. So now, let's have A go to 0 here. So now you might be tempted to think, okay, this can generate a string of at least a 0, because we can get our start to our A to our 0, but since we can't ever get rid of that B, this actually doesn't generate anything. And we'll see how this tells us that.
Okay.
So, first we do mark all our terminal symbols, in this case it's just 0. Then, for every rule A goes to whatever, mark A if all the whatevers are marked. A goes to whatever, all the whatevers are marked A. And now, our A is marked. So we go and we're going to mark it in all the rules where it appears over here. Once again, repeat this step until we don't mark any new symbols. So now we have everything to the right of A is marked, so now we're going to mark A here, but we already have all those A's marked. Repeat again, look to the right of everything, is it all marked? So we don't change anything. Did we mark S? No, we didn't mark S. So the language is still empty. Since there was no way to ever mark that B, we could never mark S. Which is,
for that matter. Yeah.
Or B, but since we couldn't ever mark our start symbol, then the language is empty.
So you start from where you succeed and work your way back.
Right, because if we tried to generate this thing, so replace S with AB, we could ultimately replace the A's with zeros. We'll never be able to get rid of that B.
Yeah.
And you have to get rid of all your variables in order to consider a string generated. So now let's go over one where it will be empty, and I'll still try and make it a little bit weird so that we can see everything happening. I'll have A goes to, this time we'll do CC, whatever. A goes to 0, and we'll have B goes to 1, and then we'll have C goes to 2. We're not a binary, well, we can just have it go to 1. Doesn't matter. Or we'll have it go to 1, or it goes to C twice. Let's do that. No, that's still not doing what we want. I don't know, I need to demonstrate the loop outside of it. We're overthinking it. So let's just look at this one. This one we know will ultimately work. Because we can take our S, replace it with A's and B's, and all our A's we can ultimately replace with, oh, I have A goes to C, I need C goes to something. Put that with a C, we'll be fine. Okay, so A's goes to C's goes to zeros, and B's ultimately goes to more B's, ultimately goes to more ones. Now we know it's possible to get rid of every string. Do a quick example, we could have S goes to AB, we could do the A goes to CC, so we got CCB. We can do the B there goes to 1, so we got CC1, and then replace the first C with a 0, so 0C1, and then replace the second C with a 0, so 001. Okay, we got a string 001. So it is possible, we know it's possible from just testing it. Now let's see it through our algorithm here. First thing we do, mark all the terminal symbols. So mark the 0, mark the 1. Next, for every rule of the form A goes to whatever, mark the variable if all the stuff on the right hand side is marked. 1's marked, so mark B, C's marked, so mark C, and so now I'll mark our B's and C's up here. Alright, repeat this step again until nothing is marked. B has everything to the right of it marked. A has everything to the right of it marked, so we can mark the A there and the B there. Repeat again, S has everything to the right of it marked. Mark S. Repeat it again, nothing new is marked, except that the start symbol was marked. It is not marked. The start symbol is marked, so we don't accept this one. This language is not empty.
I see. And all we care about is the start symbol. If there's some other symbol that never gets used, it doesn't matter.
Yeah, it doesn't matter. That's why I was trying to set up some loop at the bottom that is disconnected from everything.
Yeah.
Yeah, so we don't care if there are some symbols that don't get used. All we care about is, was it possible to get from terminals to the start?
Yeah.
Going backwards. And if you can do that, then you could have gone forward to it.
That's cool.
It's just easier to think about backwards. Okay, so that's how that proof works. And then finally, we're going to prove that every context-free language is a decidable language. So we've always been drawing this picture and we said, hey, all the context-free languages are decidable languages. Now we're actually going to prove it. Make sense? Okay, every context-free language, context-free language is a language generated by context-free grammar. Oh, I just call it context-free there. So you should be good. So every context-free language is decidable, that's what we're proving. So let A be some context-free language. Since A is a context-free language, there has to be some grammar that generates it. That's the definition of a context-free language. So let A be a context-free language, then there has to be some context-free grammar that generates it. We'll call that grammar G. So G, whatever it is, it's the grammar that generates the language A. Now we need to construct a Turing machine that accepts a string W if and only if G generates that string. right? We're trying to show that A is a decidable language. So I need to come up with a Turing machine that says yes, if and only if the string is in that language. And says no, if and only if the string is not in that language. So that's what my Turing machine, MG, here needs to do. Now, I know the language that I'm trying to decide, which means I know the context-free grammar. I know that's a context-free language, so I know that there's an associated context-free grammar. So, our machine M, we call M sub G, reminding us of the fact that we already know what G is. We have access to this information ahead of time. If I tell you to build a machine that recognizes this language, you know the language that you're trying to recognize. So M sub G, reminding us, we already know information about G. This machine needs, anytime I give it a W from A, it needs to say yes. Every time I give it a W not from A, it needs to say no. So this machine just takes some input W. And it's just testing, is it in the set A? How do we do that? Well, we just simulate our grammar G and W on M4. Remember what M4 was? Going back. No, on M5. Forgot we changed all our subscripts. On M5. What does M5 do? If you give a grammar and a string, it tells you yes, that grammar generates that string, or no, that grammar doesn't generate that string. We already built that machine. So that's all we need to do. We just use that machine, we have that basically that subroutine. So you give me some input string W, I already knew G, I can now just simulate W on G, using the machine we already built. And if that machine says yes, G generates W, then I say yes, W was an A. If this machine says no, G does not generate W, I say no, W was not an A. Make sense? Gets kind of hard keeping track of these subroutines that you already built sometimes. Okay, but if we're good with that, that ends the decidability section, and we can move on to the next section, undecidability, if you guys are up to it. Or we can go until next time.
By the way, did class end at 8 last Saturday? It's not class.
It ended early.
Okay.
It ended early because I didn't have the stuff pre-written, and it was just going to be a bunch of theorems, and I didn't want you guys to have to just watch me write a bunch of theorems.
I see. I'm here. I'm ready to
Want to keep going?
use that one.
Yeah, sure.
So this is probably the most interesting section in the book. Stupid thing. Oh well, I'll just have to.
So everything underneath a Turing machine is basically decidable. Is that correct?
Yes. Everything that finite state machine can do or a push-down automata can do, a Turing machine can do.
Huh. Do you know if they use the concepts of finite state automatas and stuff like that, that they use that in a lot of electronics or things that aren't necessarily?
We used them in compilers a lot to help us think through problems. And then, I don't know if it's a thing anymore. It used to be a thing that you'd design finite state machines for things like a stoplight. But now microprocessors are so mass produced that nobody bothers anymore.
So everything's a Turing machine, you know, it doesn't need to be.
I would guess that, except for really, really specialized conditions, we're pretty much just using Turing machines for everything now.
More often than you think we're not.
Really?
Yeah, like, I know like one example is HDMI are specialized chips that are state machines. They're like they only do that one thing. Like in most modems are that way. Pretty much anything that's very cheap and does a very specific
Modems
thing.
still make sense, yeah.
And like those crypto miner graphics cards and stuff like that, I think that they literally go down to the wire.
Yeah, I think ASIC miners are actually not Turing complete, which is interesting.
Oh, interesting.
So they're not Turing machines.
And
Right, so-
the Enigma machine,
Just state machines.
you would consider, well, it would run forever. I don't, maybe you don't.
Enigma?
Do you know if the Enigma was considered a Turing machine?
I mean, it definitely wasn't Turing complete.
Okay. So it was somewhat, then it was decidable, essentially.
Yes, it would have been decidable. You could decide the things that that machine would have said yes to, and the things that that machine would have said no to.
Yeah.
Because, yeah, it was just checking a finite number of combinations. Just saying yes or no. So, yeah, I'm pretty sure you could model that with just a finite state machine. Crap ton of states, but you just need a state for each of the possibilities navigating around. I don't see why not. But yeah, I guess that there's probably places where engineers are being super, super clever and utilizing every little bit of material that they have where they're still using state machines
It's mostly a power thing.
to reduce on the wiring. Power thing?
Yeah, if you build a specialist chip, then you can reduce your power consumption by whole orders of magnitude, right?
Yeah.
What was one of those terms called? It's the one where it shoots everywhere. Can't remember what it's called.
Non-deterministic.
Non-deterministic. It reminds me a lot of if you were to shoot electricity through a whole bunch of wires, and they were all hitting different stuff all at the exact same time. And all you have to do is at the very end get some light that turns on and say yes, it's working. You know.
Yeah, non-deterministic is, the way I always think about it is you're doing every possible combination in parallel.
That's the thing, but it's like if it was like an electric bolt that shot through a bunch of the stages and, eventually hit that state somewhere. I don't know.
If electricity through wires works for your intuition,
That's how it works really well for me.
Then-
It's very simultaneous.
that's what works.
Yeah.
Yes. Yep. Everything all together in parallel.
And that would be extremely efficient if you think about it. To do very large amounts of operations all simultaneously, where nothing's waiting on the other thing. It's kind of like Node.js.
You should look up asynchronous computing.
Say it again.
You should look up asynchronous computing.
Asynchronous.
I-
Yeah, it's
I
asynchronous.
had a professor who he had his PhD in asynchronous computing, and it's exactly what you're talking about. It's very interesting.
I know a little bit about it working with Node and JavaScript, but I would really love to get into it more because it's by far the most powerful and fastest way to program.
Problem is that as far as I understand, you can't make an asynchronous Turing machine. You can't make an asynchronous Turing machine. That's one of the fundamental issues with them is that
Really?
they are not Turing complete.
I guess because, there's no guarantees. I guess that's what comes down to.
So as long as you're going to a different machine or a completely different isolated situation, then you can do asynchronous. Kind of like how
If one situation fails, there's no way for another situation to know.
Yeah.
I might be wrong. You might be able to.
Well, I mean, take for instance,
This is what
there's
happened.
multi-threading, but that's where completely separate processes. Or a graphics card is somewhat asynchronous, if you think about it.
Well, remember that when you're talking about on a single computer, all that stuff is just an illusion.
Yeah. Well, here's
It
the.
all comes down to just one ALU,
Uh,
gusser. And so you're breaking up those processes and you're basically telling your computer, if you tell your computer order doesn't really matter with these processes, then it can be more efficient. But on a fundamental level, your computer is still just doing one computation at a time. It's not doing multiple.
Okay.
Yeah.
Well,
Like at least the way that he was describing asynchronous computers that he worked on didn't have a clock in them, right? And so they are very deterministic in that you put in your input and everything just kind of happens all at once, kind of like what you're saying.
huh.
And so they are very efficient for the processes they work on. It's just that it's really hard to generalize them to work on anything. Otherwise that'd be sweet, because you could just be here's here's the hash that I'm trying to find, and it would simultaneously try all possibilities and be like, oh, like, you know, like totally ruin modern encryption and things like that.
I think asynchronous is useful in almost every process, to be honest.
But all asynchronous things that we interact with are, like Dark said, complete illusions.
Yeah. Okay. And well, take for instance, JavaScript isn't technically asynchronous.
Yeah, it runs on one single
It
thread.
always does one thing at a time, but instead of waiting around for other operations to finish, then it will pick those up later. But graphics cards aren't that way, and stuff like that. So I don't know.
No, graphics cards are absolutely that way. It's just that you can fill your registers up with a whole bunch of things that you want to do in one clock cycle, then you do them all in one clock cycle.
Yeah.
So it's,
Right.
yeah, it's not so much that
It's like replacing multiplication with matrix multiplication.
But you're not multiplying one at a time, right?
Well, you're multiplying the whole matrix, but it's still
Every clock
one
cycle.
step. So it's just that it's harder to reuse matrix multiplication. It's so easy to just use multiplication. So that's why you can't just replace your ALU with just a graphics card. You still need just regular multiplying. But if you know very specialized, hey, I'm going to do this math calculation where I need all these values multiplied by all these values, then the graphics card is fantastic for that, like you do with graphics.
Interesting. So it gets a little more complicated when it's just completely different. I don't know.
Yeah. So it's not, like, I guess one way to think about why a graphics card is not asynchronous is if it was asynchronous, then as soon as the input showed up, it would immediately start multiplying. That's not how it works. All the registers are filled, and then they all multiply together in one step.
Oh.
So it still is synchronous, it's just that you have, like, your bandwidth is very wide. So you're,
Yeah, that's interesting.
Alright, moving on now to undecidability. So we proved that all those things were decidable. We proved that we could create these algorithms that said yes every time the answer is yes and no every time the answer is no for all those problems. Now we're going to move to undecidability. We're going to show that there's actual questions that we can ask that you can't say yes every time the answer is yes or no every time the answer is no. So the problem that we're mostly going to be talking about is the acceptance problem for Turing machines. We already did for DFAs, we already did for context-free grammars. Now we're talking about for Turing machines. So the acceptance problem for Turing machines, what's that? It's going to be the set of all encoded order pairs of the Turing machine and some string W, where n is a Turing machine that accepts string W. Ultimately, we would want to say, can we create some algorithm such that no matter what Turing machine I give you and what input string I give you, can you always determine, yes, that Turing machine will accept that input, or no, that Turing machine will not accept that input? Or something that any such algorithm is impossible to make. Not really, really hard, not maybe one day we'll be clever enough. No, it's impossible. The same way that 1 + 1 = 3 is impossible. So that's our question. Is the acceptance problem decidable? We're going to prove that's not decidable. But it is recognizable, and that's relatively easy to prove. So we're going to prove that the acceptance problem for Turing machines is recognizable. What we mean by that is, if you give me a Turing machine, and you give me a string that the Turing machine will accept, I can say yes. But if you give me a Turing machine and a string that it wouldn't accept, I can't necessarily say no. So it's just recognizable. I'm just guaranteeing you that if you give me a string that it will accept, I can say yes, it will accept. That's all I'm guaranteeing you. That's recognizable. Alright, so how does that work? Well, we just use Turing's universal Turing machine. So let U be the Turing machine that on input M and W, we simulate W on M and accept if M accepts. Otherwise, we reject. Now there's a problem with that. Because wouldn't that be deciding ATM? So I say, here's what my machine's going to do. You give it some input, some Turing machine and some input W. What am I going to do? I'm going to run W on M. Just run it. Run W on M. And if M accepts that input, I'll accept. And if M rejects that input, I'll reject. The problem with that logic is we don't know that what if M never stops? We're not guaranteed M's going to halt. What if it goes into an infinite loop? So we can't say otherwise reject here. All we can say is if M does accept the string, then we can accept. To say otherwise reject there would mean that we're guaranteed M halts. But we don't know M halts. A Turing machine, it can compute some infinite process. That's the big difference between it and like a push automata or like a grammar. The whole trick with our grammar problem, acceptance problem there, is we were able to put some upper bound saying after this many computations, we for sure should have an answer. And we can do a similar thing with DFAs. After this many computations, we should for sure have an answer. With the Turing machine, there is no upper bound. We can't ever say after this many computations, we should for sure have an answer. So we're never guaranteed that these things will halt on some input. Maybe they go into an infinite loop or crash or whatever. And so it was bad logic for me to say otherwise reject. But if it does accept, then we can accept. Because that means it stopped. So that's as much as we can say. So U takes some Turing machine and some input. It can run W on M. If M says accept, we can accept. If it does, it might run forever. It might also reject, and we could reject in the cases where it rejected, but it might also run forever. So we're not guaranteed that we'll always accept or reject. So that's the big difference there. So then U recognizes the acceptance problem, but doesn't decide it. And that's going to be the big one. The whole goal of this chapter is working up to the idea that this can't decide it. It can recognize it, we can recognize that, but we can't decide that. And that's going to be our main problem that we use after this chapter to prove other problems can't be solved.
So there's a recognizable, and then there's decidable, and then there's like a third thing where if I give you
Yes.
and you're like, I don't.
So there is a whole hierarchy to, outside of computation theory, we would call it set complexity.
Okay.
And there's a whole hierarchy of set complexity, and we're just picking some interesting ones that computers happen to care about. And so yes, we will prove, and it will actually be the complement of this language, that that's not even Turing recognizable. This thing's complement isn't even recognizable. It's not decidable and it's not recognizable. It's something completely different. And we'll prove that.
Yeah, let's see that.
So yeah, so there is, outside this bound, we just stopped at recognizable, but there's all sorts of other hierarchy out here. This. There's a whole hierarchy still. And we just, for the purposes of this class, we just don't care about the rest of that hierarchy. Okay. So we basically need to put a pin in this, go do a bunch of other math, and then come back to it. So putting a pin in that. And we need to introduce the method of diagonalization, introduced by Georg Cantor. Now, seems unrelated, but turns out it's very related. He got stuck on a question, and the question is, what does it mean for two sets to be the exact same size? How can we know that two sets are the exact same size? And the naive way that you might think about it is, well, we just count one set, and then we count the other set. If they have the same count, then the two sets are the same size. And that works, and that's a perfectly valid way to determine that two sets are the same size. But do we really have to go through all that work? Imagine you were sitting in a room, a crowded room full of people, and you notice that no one in the room is deformed. You instantly know that the set of all right hands is equal in size to the set of all left hands. You have no clue how many right hands or left hands there are, and yet you know that those two sets are equal. So while counting the size of two sets is one way to determine if two sets are of equal size, it's not necessarily what we have to do. There's another layer of abstraction there that we can get at. And that's what he was looking for. What exactly does it mean for two sets to be the same size? Because what he wants to do is talk about the sizes of sets that are infinite. He wants to compare the set of natural numbers to a set of integers, for example. So he's trying to get at this idea of what exactly it means for two sets to be the same size, and then with that we can start talking about infinite sets. That's his motivation. So how do I know right out the door that if we're in a crowded room, and no one in the room is deformed, that there's exactly as many right hands as there are left hands? And simply because I know that every right hand is paired with only one and only one left hand, and every left hand is paired with one and only one right hand. And since we can pair all the hands off like that, then we know that they must be the same size. And we call that pairing off, in math terms, a bijection. If I can create a bijective function from one set to the next set, then those two sets are guaranteed to be the same size. Now, we talked about this in the preliminary stuff way back at the start of the class, but that was way back at the start of the class. So let's remind ourselves of some of the terminology here. So first off, reminder, here's the notation we have. F is a function from set A to set B. So this is just a notation saying we're mapping everything in A to something in B. And this can be something simple. Set A can be the letters A, B, C. Set B here can be the numbers 1, 2, 3. And it's just some mapping. A goes to 2, B goes to 1, C goes to 3 maybe. Or BF. So in this case, F is a function from the set A to the set B. So that's what this notation means. F maps everything in A to something in B. We could have just as easily had C, instead of having C go to 3, we could have had C also goes to 1. F is still a mapping of everything in A to something in B. That's what this is notation for. Now, on to. A mapping from A to B is considered on to if we use everything in B. So this is not an on-to mapping because we have C goes to 1 and B goes, nothing goes to 3. Sorry, this A here was going to 2. Bad picture. Nothing's going to 3 right now how I have it written. So right now F is not an on-to function. If I instead, A, B, C, 1, 2, 3, do A goes to 2, B goes to 1, C goes to 3. Now, since I used up all of B, the function is now on 2. Notice that if B happened to be bigger than A here, if I had a higher count, if I put a 4 in there, it's impossible for me to create a mapping from this set to this set that's on 2. Because this set's too big. So on 2 is guaranteeing that B wasn't bigger than A. Is one way you can think about it. So on 2 guarantees us that B isn't bigger than A. We could have had B smaller than A. I could have had, get rid of that 3, and could have had C goes to 2 as well. This is still on 2. So, function from A to B, on 2 is guaranteeing us that B isn't bigger than A, and then this one-to-one part is going to guarantee us that A isn't bigger than B. One-to-one means that in your function, every left-hand element is paired to one and only one right-hand element. So I can't have A goes to 2 and C goes to 2. Since A went to 2, C has to go to something else if I want it to be on 2. So I'd have to have some other element here, 3. And that's what we mean by a bijection. So a function f from a set A to set B is called a bijection, provided that it's on 2, meaning we use all of B, and 1-to-1, meaning everything in A goes to one and only one thing in B. I can't have A goes to 3 and C goes to 3. That's a bijection. Now, our definition of two sets being the same size, now that's not actually the word we use cardinality. The cardinality of the set, the size of the set. It's just the proper term. So two sets A and B have the same cardinality, or size. We write that as the size of A is equal to the size of B, provided that there exists some function f from A to B, such that f is a bijection. If I can create a bijection between two sets, then they're the same size. And that's exactly what we do with the example when you have a crowd room with people. Create a bijection between their hands. We pair each hand to one and only one hand. Every hand gets paired, and every hand is paired with only one hand. And so you know instantly that those two sets have to be the same size. Okay. So that's what needs to be the same size. Now let's do some examples with this. Go ahead.
What does cardinality mean in this context?
You can think about it as size. Two sets A and B have the same size, written this way, provided that there exists a bijection between the two sets.
It's a term used in my scale indexing, so I wanted to just make sure I understood what that meant. But if you're just saying it's how much is in that container, or that set, that's what cardinality means. Okay, cool.
Yep, that's exactly what it means. Okay, so now that we have a proper definition for what it means for two sets to be the same size, to have the same cardinality, let's do some examples. So let E, capital E here, be a stand-in for e is equal to the set of all natural numbers, all little n in the natural numbers, such that n is even. So e is equal to all the even natural numbers. 0, 2, 4, 6, 8, 10. Not all the even integers, all the even naturals. I'm going to prove, then, that the cardinality of the even numbers is equal to the cardinality of the even naturals is equal to the cardinality of just the naturals. In other words, if you have the naturals and you get rid of all the odds, you didn't change the size of the set. Kind of weird.
It's infinite?
Because it's infinite.
Okay.
When you cut infinity in half, you didn't really change it. Some intuition for how to think of that. So, we're going to prove that. How do we prove that? We need to come up with this bijection. Now, I don't know how much you guys want to get into the nitty-gritty of how you do these proofs. I don't know. Are you already pretty comfortable with onto and one-to-one? Or are those new for you?
I've never heard the term onto, but I get the concept that B can't be bigger than A.
Alright. I'll go over the nitty-gritty of how we do one of these proofs. I think you could probably just get from the intuition. I'll go over the nitty-gritty once. If that feels like overkill, I guess I only go over the nitty-gritty once, so maybe we'll just do it. Okay, so let's prove that the evens are the same size as the naturals. Proving that the cardinality of the evens is equal to the cardinality of the naturals. I need to come up with some bijection and prove that's a bijection. That's basically all I need to do. If I can find some bijection between those two sets, then they must be the same size. Some way of pairing them up. So I just need to come up with some way of doing that. And I'm going to do probably the obvious one. Let f be the function from the naturals to the evens by f of n equals to n. In other words, maybe create a table over here for how I'm doing my pairings. Here's my n, here's my f of n. I can plug in any natural you want, and I'm claiming that this will spit out every even natural. So if you plug in 0, when I plug 0 in for this function, I get 0. If you plug in 1, when I plug in 1, I get 2. When you plug in 2, I get 4. When you plug in 3, you get 6. When you plug in 4, you get 8. And I think you get the picture here. And notice that on the left-hand side, we will eventually write out every single natural number. If we follow this pattern, 0, 1, 2, 3, 4, we'll eventually write every natural number. On the right-hand side, we will eventually write every single even natural number. And so we will pair every natural number with every even natural number. You cannot find a natural and an even natural that we don't pair. Pick as big a number as you want, we eventually pair it off with something.
So it's bijection?
So yes, this right here is a bijection between these two sets.
Okay.
Everything in here is paired with one and only one thing in here, and everything in here eventually gets paired with. Pick something in here, I can find something in here that pairs with it. Pick two things in here, I can show you that they map to different things in here. So you don't have two things map into the same thing. I'm going to prove that explicitly. Here's why I was worried it might be kind of overkill. So, oh shoot. Image of a function.
Say that again?
Image of a function, is that new notation? We went over it right at the beginning of the class, but it's a lot to take in the preliminaries.
Yeah, could you remind me?
It's basically all the right-hand elements that we pair with. Everything that f pairs with over here.
The outputs or
All the outputs.
It's kind
Yes.
of like the range.
Right.
It's identical to the range.
Oh yeah, I now remember now.
Exact same thing as range.
Yep.
Perfect. So range of a function, image of a function, identical. It's just, it's one of the, I don't know why we do that. Lower level textbooks, they call it range. Higher level textbooks, they call it image. And it's just the way it is. This book calls it image, so I'm sticking with what this book uses. But yeah, think range and you're perfectly fine. Okay, so first thing I need to show, if I want to show that it's on 2, to show that the function's on 2, I need to show that everything in B gets used, or everything in E here gets used. So I need to show that E and all the things that get used are the same set. All the right-hand elements that get used, or the range, and the set that we're talking about over here, in this case E, are the same set. That's what I'm showing. If I can show they're the same set, then it's on 2. If the range is everything, it's on 2. So that's what we're going to say here. So observe, first off, that the range is a subset of the evens, by definition. And so now I just need to show that the evens are a subset of the range. And if two sets are subsets of each other, they're equal. It's like if A is less than or equal to B, and B is less than or equal to A, those two numbers are equal. If A is a subset of B, and B is a subset of A, those sets are equal. Same thinking. So I already know that my range is a subset of the evens. That's just by definition of a function. We're mapping naturals to evens. I need to show that my evens are a subset of my range, and we're done. Because then they're equal. Good? It's like I already know that this is less than or equal to this. If I can show that this is less than or equal to this, they're the same.
I'm having a hard time seeing how the range of the natural numbers
Let me,
is a subset.
let's actually draw out a piece of this function so that we can make sure that all our picture is mapping up with our actual variables here. That's going to be an infinite set, that's going to be an infinite set. Over here we have E, all the evens. Over here we have all the naturals. We have 0, 1, 2, 3. Over here we have 0, 2, 4, 6. And our parent is just going straight across like this. Okay, just so that when I talk about the picture, everything matches up. The image of F is all the things over here that get used. Maybe for some reason, and somehow I define my function, it's not the way that is, but maybe I accidentally defined it in such a way that 0 also mapped to 2, and didn't ever actually map to 0. Maybe I messed up somehow. And so we had a picture like this. In this case, all the right-hand elements that get used, the ones that get used, the range, is not everything. We miss 0. So I already know that all the things that we use are a subset of E. That's given, because of how we construct the function. We're mapping things from N to things in E. So the fact that the image of F is a subset of E, that's given. That's just by definition of the function. Now, if it's also the case that all the things over here that get used, all the things over here that get used are a subset of E. Sorry, if E is a subset of everything here that gets used, then E is equal to everything that gets used.
So we're just, okay, so it has strictly to do with what's being used and not necessarily the numbers.
Which of these numbers are being used? I'm going to prove that every single one of these numbers are being used. In other words, I'm going to prove every even's being used.
That's all you're trying to prove.
To show that's on 2.
Okay.
To show that's on 2, I'm going to show that every even is mapped to. And then to show that's 1 to 1, I'm going to show anytime you have anything here, anything you pick over here only has one thing mapping to it. I never have two things mapping to something over here.
Right.
Okay, so first thing I'm showing is that pick any even you want, something maps to it. That's all I'm saying. So here's a very precise way to say it, but let's just try to give you the intuition here. So let E, little e, be any even. I'm trying to prove that for any even you pick, something maps to it. Therefore, we use all the evens. So let little e here be any random even. Since it's an even number, by definition, an even number is 2 times an integer. So let e be an even. That implies that there must exist some integer m such that e is equal to 2 times m. That's the definition of even. Now, since e is a number greater than or equal to 0, by definition of e, then our integer m must also be greater than or equal to 0. Otherwise, e would have been negative. So that means our integer m must be a natural number. Because it's an integer greater than or equal to 0. That's exactly what the naturals are. So that means that when I plug m into my function, I get e. Which means e is in the image of my function, which means that the evens are a subset of the image of my function. Now, maybe I'll lose you in that a little bit, but what did I just barely show? I shall pick any even you want over here, and it gets mapped to. It's in the image of our function. It's in the range. Right? So maybe the subset stuff after that's throwing you off, but if you just understand the intuition up to here, you're probably good. So since every even gets mapped to, then we're on to. Okay, so that's how we show it we're on to. Now we need to show it we're one-to-one. What does it mean? How could we make this function not one-to-one? The way that we could have this function not be one-to-one is if we had a scenario where 0 went to 0 and 1 went to 0. I can't have two different things here go into the same thing here. Alright, how am I going to show that? I'm going to show that anytime you pick two things that are mapped to, they're always distinct. Anytime you pick two things from over here that are mapped to, they're always distinct. They always came from different inputs. Okay. Let's see. Maybe there's how's a better way to say that? I'm going to show you that anything that you pick over here, the things that map to it are always the same thing. That's probably a better way to say it. So here's where I'm going to start. I'm going to start, let m and n be any two things from your domain, any two things from over here, such that they map to the same thing. So maybe I pick 0 and 1, maybe I pick 0 and 0. M and n could be the same thing here. If our function's one-to-one, m and m are going to be the same thing here. So I'm going to prove that m and n are the same thing. So I'm going to prove that if you pick two things that map to the same thing, then you really pick the same thing twice. If our picture looks like this, I could have picked 0 and 1. Those would be two things that map to the same thing, but those aren't the same. So it's not one-to-one. If it was one-to-one, so it looks like this, then anytime I pick two things that map to 0, the only things I can pick that map to 0 are 0. I'd have to pick 0 twice. That's the only way I could pick two things that map to 0. That's what we're showing. So we're going to pick any two things from over here, m and n, which map to the same thing. Pick any two things such that when you map them, you get the same thing. Now, by definition, f of m and f of n, just using our definition right here, when you plug m into that, you get 2m. When you plug n into that, you get 2n. So if f of m is equal to f of n, then 2m is equal to 2n. Divide both sides by 2, you get m equals n. So I just barely showed, if the outputs are the same, the input had to be the same. Which means it's one-to-one. Alright. Bit technical with how we prove those things about functions, but that's how we do it. From here on out, we'll just rely on your intuition. So I showed it's onto, I showed it's one-to-one, therefore f is a bijection from the naturals to the evens. So they have the same cardinality. That's how the proof would work. Alright, proof that the integers have the same cardinality as the naturals. So in general, the way that we prove this is we just see, can we come up with some listing that does it like this? If I can come up with a listing that does it like this, then coming up with the function, then if I can list it like this, then I know some function exists, and it's just a matter of being clever to come up with the function and then prove that it's onto and one-to-one. Intuitively, if I can list it out like this, so I'll eventually list everything here and I'll eventually list everything here, they're the same size. So from here on out, we're just going to think about pairings like this and not go through all the work of proving that our function that we choose is one-to-one and onto. So this time, I'm going to map the natural numbers to the integers. Natural numbers to the integers, and I'm saying here's the function that does it. I'm just going to say that this is one-to-one and onto now. We're not going to prove it. So what do we do? So writing over here, our naturals, we still have our naturals as before. 0, 1, 2, 3, 4, dot, 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 all the naturals. How does my pairing work? If n is even, I output n divided by 2. If n is odd, I add 1 to it, divide it by 2, then make it negative. So since 0 is even, in this case n is even, I divide it by 2. 0 divided by 2 is 0, so f of 0 would be 0. Okay, let's plug in 1. 1 is odd, so I use this expression. 1 plus 1 is 2, divided by 2 is 1, negative 1. Now plug in 2. 2 is even, so I use this top one. 2 divided by 2 is 1. Now plug in 3. 3 is odd, so I use this bottom one. 3 plus 1 is 4, divided by 2 is 2, make it negative, negative 2. And when I plug in 4, I'll get 2. Now we've got negative 3, 3, negative 4, 4, negative 5, 5. And you see the pattern. And so intuitively you can see we map every single natural number to one and only one integer. So the cardinality of the natural numbers and the cardinality of the integers are the exact same size. And we can do a full formal proof, proving it's onto and one-to-one like this, but it gets kind of tedious. All right, let's try a more surprising one. The rationals. The rationals are any possible fraction you can make. If we look at all the rationals between the numbers 0 and 1, there's infinitely many. We have 1/2, 1/3, 1/4, 1/5, 1/6, 2/3, 2/5, 2/7. There's an infinitely number of rationals between just the number 0s and 1. Yet we're going to prove that there's just as many rationals as there are naturals. Crazy. Very unintuitive. Okay. For that one, here's a function that does it. In this case, we're limiting ourselves to the positives. That's what the plus there means. I'm saying I'm going to show that the positive integers, meaning 1, 2, 3, 4, 5, 6, have the same cardinality as all the positive fractions. Those are the same size. And obviously I can repeat the same things for the negatives and map 0 to 0, and that will show the integers go to the rationals. It just gets messy to include negatives on the table.
Okay.
So that's why we're limiting ourselves to the positive, but nothing special about that. Just makes it easier to write. Now if you wanted the function that did that, here's a function. What do? F on input m goes to k over j plus 1, where n is equal to, where j are the unique numbers that make this true, where k is bound between 1 and j plus 1. Now, that's a nightmare to work with. We do that if this were a real analysis course, but there it is just to show you it. It does exist. It's hairy, it's messy, we don't want to think about it. Yes, it exists. That's the function. Instead, we're just going to use similar intuition to what we have here, but this time with a table. Here's what I'm going to do. I'm going to map 1 to 1 over 1. And then on this table, I'm going to do what we call dovetailing. I'm going to come back and now start on this. I'm going to map 2 to 2 over 1, and I'm going to map 3 to 1/2. And then we're going to loop back around, and I'm going to map 4 to 3 over 1. Since 2 over 2 is the same as 1 over 1 has already been used, we skip that. We keep going this way. And I'm going to map 5 to 1/3. And then I'm going to loop back around and keep going. If we expand this table out, I will eventually list every single positive rational number. Any positive rational number you can think of, I will have eventually written it somewhere on the table. And in this process of, think about it as like coloring in the area, if we keep coloring in the area like this, I would eventually reach that number. So I would have eventually found some positive number that I mapped it to, or that I mapped to it. And so that's a fancy way of saying there is a way that you could actually list out all the rational numbers. There's a logical, there's an algorithm you could come up with for listing out all the rational numbers. That's possible to do. With the real numbers, not so much. But with the rationals, as surprising as it is, you can come up with some general pattern. And you already see what it is. Do all the ones with 1 and 1. Now do all the ones with 1 and 2. Now do all the ones with 1 and 3, and then 2 and 3. And then all the ones with 1 and 4, 2 and 4, and 3 and 4. And you keep going like that, and you'll eventually list out every single rational number in some pattern. So since there's a way to list it, it's the same size as the naturals. That's the intuition there. Some quick corollary. What did we show? we showed that the naturals have the same cardinality as the integers have the same cardinality as the rationals. So you look at just your non-negative whole numbers, that's the same as all whole numbers, that's the same as all possible fractions you can write down. Turns out there's still no more. Even though with all the possible fractions, you can get an infinite number between 1 and 0. And it still didn't increase the cardinality of the set. It's insane. But when we get to R, the real numbers, now we did for sure increase the cardinality, and we'll prove that. And that's going to be our next proof here. Just a matter of quick definition. A set is countable provided that it is finite, doesn't have infinite elements, or its cardinality is the same as the natural numbers. So the natural numbers, well, the natural numbers not including 0, if you do 1, 2, 3, 4, etc. We often call those the counting numbers. And a countable set is a set whose cardinality is at most the countable numbers. So that's where that terminology comes from. And then, otherwise, if it's not finite, and its cardinality is not the same as the natural numbers, then we call it an uncountable set. It can't be counted. And we're going to show that the real numbers are one of these uncountable sets. There's no way you can count the real numbers. There's no way that you can come up with some way of listing out the real numbers and list them all. No algorithm for doing that. That's what we're going to do over here. I think I need to move my camera like 6 inches. Okay, I think I got it. All right, so that's what we're going to do next. Prove that R is an uncountable set. There's no way you can list these things out. We're going to do this, but we're going to do a proof by contradiction to prove this. We're going to assume that you can list out the real numbers and show that that leads to some impossible worldview. So if you're doing it implies something impossible, then you can't do it. Make sense?
Like, if doing it implies that 1 equals 3.
Right.
Yeah.
If we therefore 1 equals 3, that's a contradiction. 1's not equal to 3. So your assumption, whatever you assumed, is false. So we're going to assume, by way of contradiction, that the set of real numbers is countable. Now, for the sake of making the proof a little bit nicer, we're not going to use all the real numbers. We're just going to look at all the real numbers between 0 and 1. So I'm going to prove that there's an uncountable number of real numbers if we just focus on between 0 and 1. Forget all the real numbers. Let's just focus on the real numbers between 0 and 1. I'm going to show you that it's still uncountable. That there's still way more of these things than there are natural numbers.
Or more? You're saying there's more?
Way more. There are way more real numbers between 0 and 1. The way we write that set is open parentheses 0, 1. That's shorthand for all the real numbers between 0 and 1.
What?
0.5 is in there.
Yeah, I got that.
Pi force is in there.
How is it more than all the real? I thought they have to be equal.
This is more than all the naturals.
That's what I meant. How is it possibly more than all the naturals?
So all the naturals are just 0, 1, 2, 3, etc.
To infinity.
Right. 0.5 is not natural.
Yes.
Okay, so I understand that.
I still understand why.
So the real numbers, all the numbers between 0 and 1, every possible real number, not just the fractions, including all the numbers that can't even be written as fractions. There's way more of those things than there are natural numbers, than there are fractions, than there are integers, even though they're both infinites. That's the whole reason Cantor came up with this new definition for how we talk about the sizes of things. He wanted to compare sizes of infinite sets and come up with some way of doing it. So to show that this set is in fact bigger than the natural numbers, I'm going to show you that it is impossible for you to pair all the natural numbers with an element in the set. You'll always miss one.
It's kind of like a two-dimensional approach on, I don't know.
No, it's not even just a dimensional thing, because the rationals did that. They went two-dimensional. And you could come up with the notion of a three-dimensional fraction, which had a numerator, a denominator, and a denominator, whatever, make up some word. And it would still be the same as the naturals. And the way you would prove it is using a cube. And if you came up with some notion of a fraction that was a combination of 4 numbers, it would still be the same, and the way you prove it is with doing the same process with a 4-dimensional cube.
Could you come up with a cube that's infinite dimensions? Or would that be cheating?
That's cheating now.
Okay.
So as long as it's finite dimensions, it's going to be smaller. Once you say infinite dimensions, which infinite are you talking about? And so to say infinite dimensions, it turns out, is kind of a meaningless thing to say.
The infinite is at least as big as the rational numbers.
But we will show how to get from one set to the other set, and it turns out take its power set. And that gets you from one infinity to the next. And we'll try to get some intuition for that. Kind of dense stuff. We might have to stop after this proof, and then maybe restart next time with this proof. Probably a good place to and pick up. Because it's pretty mind-blowing the first time you come across this stuff. At least it was for me. I don't know, maybe it feels natural to you. Okay, so make sure we understand the problem. This is a stand-in for all the real numbers just between 0 and 1. That's all it is. I'm going to show that it is impossible for you to come up with a bijection, a function, from the natural numbers to all the real numbers between 0 and 1. No such function exists. That's what we're going to prove. So assume by way of contradiction that it is countable. Or in other words, assume by way of contradiction that Partly stays up all night and he's able to come up with one of these functions. And I'm going to show Partly, nope, I don't care what you thought of, you're wrong. You didn't do it. So let's pretend that Partly says, I've got one, I came up with it. Here's what I'm going to tell you Partly to do. I'm going to say, look at your functions. And it's going to list out something like this. It's going to say 0 goes to some number between 0 and 1. It's going to say 1 goes to something, 2 goes to something, 3 goes to something, 4 goes to something. You have some mapping. The concrete numbers we have here don't really matter. It's just easier to see this by way of example. I'm going to give you the example of what we do and then read you through the proof, because it's easier to do that way. I say, I'm going to tell you how to come up with a number that you for sure didn't get. I'm going to show you one that you for sure missed. And we're going to start with 0 point, since it's between 0 and 1. 0 point. And I'm going to say, whatever you map 0 to, look at it. We'll use computer science indexing here. Look at its 0th decimal place and add 1. So your 0th decimal place was a 1. So we're going to start this with 0.2. Now I'm going to say, for your first one, look at its 1th decimal place. If it's a 9, we replace it with an 8. Why don't we replace it with a 0? That's technicality, but we're going to replace it with an 8. Now on 2, go to its 2th decimal place and add 1. So this is going to be a 2. On the 3, go to its 3rd decimal place and add 1. That's going to be another 2. Keep doing this process. Dot, 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 dot. This new x that you generate, you did not map anything to. You didn't map 0 to it because it's different in the 0th place. You didn't map 1 to it because it's different in the 1's place. You didn't map 2 to it because it's different in the 2's place. Dot, 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 dot. For any natural number you pick here, I can show you the decimal place. For any natural number you claim maps to that number, I can tell you it doesn't because it differs in the nth decimal place from the thing you actually mapped it to. So here's a number that you missed, guaranteed.
Is it kind of like saying that you always missed a number between the n0 and the n1? There's always a number in between those you had to have missed.
Right. I'm saying for any bijection you think you came up with, I can always come up with a number that you for sure missed. You missed a lot more than that number. I'm just coming up with one that you missed. Because you actually missed infinitely many. And a whole different type of infinitely many.
Okay.
So, that's what the proof's going to walk through here. That intuition. So, assume by way of contradiction that someone is able to come up with a bijection. We know it's impossible. Let's assume that they did. We're going to construct a real number x such that its whole number part is 0. So we start with 0 point. And x's nth decimal place is 8. If f of n's, the number that you have listed here, is a 9. So if the nth decimal place that you listed is a 9, then when I'm generating x, I'm going to do an 8. So in that case, it was right there. And 1 more than f of n's otherwise. Otherwise, if your nth decimal place isn't an 8 or isn't a 9, then I'm just going to add 1 to it. That's how I'm going to generate the sets. Okay, that's the messy part of this. Now, observe that for any natural number you choose, that natural number does not map to x, since their nth decimal places will differ. So I just barely showed that for anything you pick on your left-hand side, it doesn't map to this thing. So I found something in the set over here that you for sure didn't map to. So we're not on 2.
Okay.
That's the logic there. So since x is not in the image of your function is not on 2. We assumed your function was a bijection, which means we assumed your function was on 2. I showed you that implies your function is not on 2. So your function being on 2 implies your function is not on 2. Contradiction, that's impossible. Therefore, your function was never on 2. Therefore, no such f exists. So even when you just focus on the real numbers between 0 and 1, you can't do it, let alone all the real numbers. And what does this have to do with the acceptance problem? Seems kind of weird. But it all comes back to it. Anyways, so I think we'll end with that proof. We'll start again with that proof next time, because then we're going to do a similar proof except for with binary expansions.
Cool.
Any questions that you want recorded before we call it? Alright, I'll try to get that uploaded as soon as I can.